Hi everyone, welcome to this session on hemoglobin and myoglobin. Let me tell you, this session will be very interesting because in this session, I will not only be telling you about structure of hemoglobin and myoglobin, I will also be telling you about the basis of carbon monoxide poisoning. How does the structure of hemoglobin and myoglobin protect ourselves from carbon monoxide poisoning? We will learn about what happens at the tissue side, what happens at the lung side. What is Bohr effect? What is Haldane effect? What is cooperative binding? What is the effect of 2,3-BPG? Why do we always say 2,3-BPG reduces the affinity of hemoglobin for oxygen? There should be an explanation behind that, right? So that will be explained. Now, what is the difference between adult hemoglobin and fetal hemoglobin? Why do we always say fetal hemoglobin exhibits very high affinity for oxygen when compared to adult hemoglobin? That concept. And not just these concepts, I will also be telling you about what happens in acclimatization and what is the effect of acetazolamide in a person who quickly climbs uphill. Because we are going to learn all about oxyhemoglobin dissociation curve in this session. So I know that most of you have many questions related to all these concepts. And if you watch this session continuously with 100% focus and attention, my assurance to you is that at the end, you will have understood all these facts and concepts. Okay. So with that introduction, let's first start with structure of myoglobin. I hope you all know that myoglobin is a monomer, which means it has got only one heme in the center surrounded by only one globin chain. And if you look at the globin chain, be it a globin chain of myoglobin or a globin chain of hemoglobin, globin chains are polypeptide chains which have 150 amino acids. Okay, and these 150 amino acids are arranged in 8 alpha helices. And those alpha helices are named from A till H. Okay, 8 alpha helices are named from A till H. And every alpha helix has individual amino acids. Those amino acids are numbered as 1, 2, 3 and so on. For example, if I call an amino acid as histidine F8, I mean to say that it's a histidine which is present as the 8th amino acid of the F helix. Do you understand this? Histidine F8 means it's the 8th amino acid of the F helix. So what does it mean when I call something as histidine E7? It's the 7th amino acid of E helix. So that's an introduction. Now in detail about structure of myoglobin, as I told you, myoglobin has got what in the center? In the center, myoglobin has got one heme surrounded by one globin chain. We learnt about the globin chain. Now about the heme. Okay. So if you expand this heme will have what in the center? Heme will have iron in the center. And this iron is surrounded by 4 pyrrole rings. And if you want to understand about the planar structure, planar structure of 4 pyrrole rings and the iron in the center, interestingly, if these two lines, if these two black lines represent the plane of the tetrapyrrole ring, iron is present in a plane below the plane of the ring. Okay, so this is heme. And this heme is surrounded by what? Globin chain. And Fe2 plus in the center is covalently attached to one amino acid of the globin chain. It is not like you've just placed heme in the middle of a globin chain. Fe2 plus in the center of heme is covalently attached to one amino acid of globin chain, and that amino acid is histidine F8. Fe2 plus is attached to histidine F8. Now, when this globin chain surrounds the heme and when it comes to the other side, the amino acid that is present exactly opposite to Fe2 plus on the other side, this amino acid is called as histidine E7. And this histidine E7 provides the hindered environment because of which we escape from carbon monoxide poisoning. First, tell me, why is carbon monoxide toxic? Carbon monoxide is toxic because carbon monoxide exhibits very high affinity to Fe2 plus of hemoglobin. So as long as there is carbon monoxide in the medium, carbon monoxide comes and binds to Fe2 plus, displacing oxygen away. Or in other words, it reduces the oxygen carrying capacity of hemoglobin, which is called as anemia. So all of you tell me what is anemia. Please remember, anemia is not just a reduction in the hemoglobin concentration. Anemia is a reduction in the oxygen carrying capacity of hemoglobin. One of the causes is reduction in the hemoglobin concentration. There are many other causes. One example is carbon monoxide poisoning, because carbon monoxide displaces oxygen away. Okay. Now, coming back to myoglobin, just imagine, right? Just imagine that nature decided to give you only heme, no globin chain at all, right? If nature had decided to provide only with heme for either transporting oxygen or for storing oxygen, to that Fe2 plus, carbon monoxide exhibits 2000 times higher affinity than oxygen's affinity. Do you understand this? If only we did not have globin chain, if there is only heme, to that Fe2 plus, carbon monoxide exhibits 2000 times higher affinity than the affinity for oxygen. When the affinity difference is so high, even the carbon monoxide that is present in this environment should have caused carbon monoxide poisoning. But we know that carbon monoxide poisoning is not that common. So how do we escape from carbon monoxide poisoning? It's only because nature decided to give us with not only heme but also globin chain. And this globin chain has come with histidine E7, which is present exactly opposite to Fe2 plus. Now, what does it do? Whenever carbon monoxide binds, this carbon monoxide binds in a plane perpendicular to the plane of the ring. Let me show you how carbon monoxide binds in green color. How many atoms are there in carbon monoxide? Carbon monoxide has got 2 atoms. So C here and then O here. So the binding of O of carbon monoxide is hindered by histidine E7, which is present exactly there. And that is why carbon monoxide affinity to Fe2 plus is reduced from 2000 times to 200 times. And this reduction is possible only because of the presence of histidine E7. So have a look at this. Okay, so what I've shown you here is, as I told you, these 2 black lines represent the plane of the tetrapyrrole ring. And in the center of this plane, we have Fe2 plus, which is in a plane below the plane of the ring. And this Fe2 plus is attached to which amino acid? It is attached to histidine F8. To this Fe2 plus, carbon monoxide binds. Okay, when carbon monoxide binds, what is on the other side of this Fe2 plus? That is histidine E7. So this histidine E7 hinders the binding of O of carbon monoxide. So the affinity of carbon monoxide to Fe2 plus within the globin chain is reduced, and that is how we escape from carbon monoxide poisoning. I can hear you all asking, then what about oxygen binding? Because oxygen also has got 2 atoms, right? So what happens when oxygen binds? Oxygen does not bind in a plane perpendicular. It does not bind like this. Oxygen binding is inclined. Okay, so the first oxygen atom binds here. The second oxygen atom binding is inclined. And that is why histidine E7 does not hinder oxygen binding, but it hinders only carbon monoxide binding. So the take-home message for all of you is, histidine E7 is the amino acid which provides the hindered environment because of which we escape from carbon monoxide poisoning. So that's all you need to know about myoglobin, which is a monomer. Let's now try to understand about structure of hemoglobin. What is that you all know about hemoglobin? It's a tetramer. So hemoglobin has got how many heme molecules? 4 heme molecules. And each and every one of these heme will be surrounded by 1 globin chain. Okay, so this is how hemoglobin exists. So in hemoglobin, this yellow color structure that is shown in the middle, those are heme molecules surrounded by globin chains. And Because it's a tetramer, because it has got more than one polypeptide chain, as I told you in the last video, right? The previous video is about protein structure. So in protein structure, I told you any protein which has got more than one polypeptide chain can exhibit quaternary structure. It is defined by how polypeptide chains interact with each other. When there is strong interaction among individual polypeptide chains, we call it as a taut structure. So what are the two types of structure which are possible for hemoglobin? Taut structure, when there is strong interaction among individual globin chains. The other one is relaxed structure, when there is weak interaction among individual globin chains. Taut structure is like you squeezing out oxygen, right? Taut structure is like you squeezing out oxygen, in the sense it helps in deoxygenation. So taut structure favors deoxygenation and relaxed structure favors oxygenation. So these are the facts that you need to know as far as hemoglobin structure is concerned. Taut structure, relaxed structure. Taut structure favors deoxygenation and relaxed structure favors oxygenation. Now, what is cooperative binding? Okay, so what did I tell you about structure of hemoglobin or myoglobin? I said there is a heme in the center. In the heme, there is a tetrapyrrole ring, right? In heme, what do you see? You see a tetrapyrrole ring, and the plane of this tetrapyrrole ring is above the plane of Fe2+, which is there in the center. And I told you that this Fe2+ is covalently attached to which amino acid of globin chain? It is attached to histidine F8 of globin chain. Okay. Similarly, you will have 4 globin chains. And all these globin chains will have what in the center? They will all have a tetrapyrrole, and this tetrapyrrole will be having Fe2+. Okay. So this is how hemoglobin exists. Now, what am I trying to explain? I am now trying to explain what is cooperative binding. So, whenever one oxygen molecule binds, okay, oxygen molecule binds in a inclined angle. Do you remember? I told you. So, whenever oxygen binds, it binds in a plane which is inclined to the plane of the tetrapyrrole ring. So, when oxygen binds to Fe2+, it pulls Fe2+ towards the plane of the ring. When it pulls Fe2+ towards the plane of the ring, Fe2+ comes along with histidine F8. So that globin chain is getting pulled apart from the other 3 globin chains. So one globin chain is getting detached from other 3 globin chains, and that favors relaxed structure. And I told you relaxed structure favors oxygenation. So binding of one oxygen molecule to one Fe2+ favors relaxed structure, and that favors binding of another oxygen molecule to the next hemoglobin. And that is called as cooperative binding. So tell me, what is cooperative binding? Cooperative binding is binding of, what is binding? Binding of one oxygen molecule to one Fe2+ favors binding of another oxygen molecule to the next Fe2+. This is called as cooperative binding. What is the reason for cooperative binding? Whenever oxygen binds to Fe2+, it pulls Fe2+ towards the plane of the ring. Fe2+ comes along with histidine F8. So that globin chain is getting detached from the other 3 globin chains. That favors relaxed structure. Relaxed structure favors oxygenation. Okay. Now, let's try to understand what happens at the tissue side and what happens at the lung side. So, closely watch this, because I'm going to ask you what is Bohr effect and what is Haldane effect at the end. Okay. So, what happens at the tissue side? At the tissue side, which concentration is higher? Carbon dioxide concentration is higher. So, this carbon dioxide passively diffuses into RBCs. Okay, at the tissue side, carbon dioxide concentration is higher. So, this carbon dioxide passively diffuses into RBCs. Within RBCs, these carbon dioxide molecules, some of these carbon dioxide molecules react with amino acids of globin chain. Yeah, so this is hemoglobin, which is a tetramer with 4 globin chains. Some of these carbon dioxide molecules react with amino acids of globin chain, forming carbamino compounds. And these carbamino compounds are negatively charged. Because they are negatively charged, they form salt bridges with anything that is positively charged nearby. And these salt bridge formation favors Toth structure. And Toth structure favors deoxygenation. Do you understand this? Toth structure favors deoxygenation. And that is how at the tissue side, oxygen is given off to tissues. Okay. Now, following deoxygenation, there is a change in the conformation of the hemoglobin molecule in such a way that histidines pKa. So, these globin chains have histidine. Following deoxygenation, there is a change in the conformation of globin chains in such a way that some of the histidine molecules which are present there, pK of which is 6, will be raised to 9. Okay, so I told you in the session on amino acid chemistry that histidine's pK is 9, which is close to the physiological pH of 7.4. But following deoxygenation, when there is a change in the conformation of globin chain, histidine's pKa rises from 6 to 9. So histidine with the pK of 9 will sense the surrounding pH of 7.4 as acidic. The cell's pH is 7.4, its pK is 9, so it senses a surrounding pH of 7.4 as acidic. To neutralize the acidic pH in the medium, histidine starts accepting H+. What does histidine do? Histidine starts accepting H+. From where does it get this H+? I told you after carbon dioxide diffuses into RBCs, only very few carbon dioxide molecules form carbamino compounds. So what will happen to the majority of carbon dioxide molecule? Most of these carbon dioxide molecules react with water to form H2CO3. That H2CO3 dissociates to form H+ and bicarbonate. It is these H+ ions which are accepted by histidine. And what will happen to bicarbonate that is formed? Bicarbonate comes out of RBCs and it reaches the circulation. Do you all understand what I'm trying to say? From RBCs, if bicarbonate come out, where will the bicarbonate be now? It will be in plasma. Okay, so if you ask what is the major form in which carbon dioxide is transported in blood, it is transported as dissolved form as bicarbonate in the blood. Okay, so when bicarbonate comes out, it is through bicarbonate chloride antiporter. Bicarbonate comes out of RBCs through bicarbonate chloride antiporter. So chloride concentration within RBC increases. And chloride is osmotically active. When chloride comes in, along with that water also comes in. So RBCs swell. And swelling of RBC is happening in the venular blood. And that is why hematocrit of venular blood. Please understand this. This is why hematocrit of venular blood is more than that of arteriolar blood. And this was asked once in INI CET. Yeah, they asked you all of the following statements are true except. One statement was hematocrit of venular blood is more than that of arteriolar blood, which is true. Why is it true? Because RBCs in venules swell because of chloride shift. So hematocrit or the volume that is occupied by cells increases. So hematocrit of venular blood is more than that of arteriolar blood. Okay, so I'm going to repeat all that which happens in the tissue side. Please listen to this. In the tissue side, which concentration is higher? Carbon dioxide. So carbon dioxide passively diffuses into RBCs. Within RBCs, some carbon dioxide molecules react with amino acids of globin chain forming carbamino compounds, which are negatively charged. Because they are negatively charged, they favor salt bridge formation with anything which is positively charged nearby. Salt bridge formation favors Toth structure. Toth structure favors deoxygenation. And this is how oxygen is given off to tissues. Okay. Following deoxygenation, there is a change in the conformation of globin chain in such a way that histidin's pKa rises to 9. When histidin's pKa rises to 9, it senses the surrounding pH of 7.4 as acidic. So it will try to neutralize the acidic pH by getting H plus from the surrounding. Okay, so do you see a reciprocal binding of oxygen? Yeah, do you see a reciprocal binding of oxygen and H plus? After oxygen leaves, H plus binds. That is called as Bohr effect. So all of you tell me, what is Bohr effect? Bohr effect is reciprocal binding of oxygen and H plus. After oxygen leaves, hemoglobin binds oxygen. No, after oxygen leaves, hemoglobin binds hydrogen ions. So that's called as Bohr effect. To tell you Bohr effect in another way, okay, what is Bohr effect? There is a reduction in the affinity of hemoglobin for oxygen. Yeah, there is a reduction in the affinity of hemoglobin for oxygen on H plus binding. After H plus binds, oxygen has to leave. That's called as Bohr effect, and this Bohr effect happens at what level? It happens at the tissue level. Okay, from where do we get these H plus ions? These H plus ions come from most other carbon dioxide molecules which have diffused into RBCs. They react with water in the presence of carbonic anhydrase to form carbonic acid. That dissociates to form H plus and bicarbonate. That H plus will be accepted by histidine. What will happen to bicarbonate? Comes out of RBCs, gets dissolved in plasma. So which is the major form of transport of carbon dioxide? Mostly your carbon dioxide is transported as dissolved form in blood. In what form is it dissolved? It is dissolved as bicarbonate in blood. When bicarbonate comes out, it is through bicarbonate chloride antiporter. So chloride gets into RBCs. That is called as chloride shift. And because of this chloride shift, water enters into RBC in the venular side. So RBC swell. So hematocrit of venular blood is more than that of arteriolar blood. So that's all about what happens at the tissue side. Please remember, at the tissue side, we see Bohr effect, which is nothing but reciprocal binding of oxygen and H plus. When oxygen leaves, H plus binds, or when H plus binds, oxygen has to leave. So there is a reduction in the affinity of hemoglobin for oxygen on H plus binding, and that's called as Bohr effect. Okay. Now, let's try to understand what happens at the lung side. Okay, so in the lung side, which concentration is higher? At the lung side, oxygen concentration is higher. This oxygen goes and binds to Fe2 plus. And this Fe2 plus is in a plane below the plane of the ring. So when oxygen comes and binds to Fe2 plus, it pulls Fe2 plus towards the plane of the ring. So Fe2 plus comes along with histidine F8. Okay, so this globin chain is getting detached from other three globin chains. This detachment of globin chain from other three globin chains in the lung side will happen by breaking all Sol bridges which are formed in the tissue side. So can you tell me what are involved in Sol bridge formation in the tissue side? I said carbamino compounds are involved in Sol bridge formation. Those Sol bridges get broken, and what is released? Carbon dioxide is released. Okay, let me repeat this. When oxygen binds to Fe2 plus, it pulls Fe2 plus towards the plane of the ring. That Fe2 plus comes along with histidine F8. So that globin chain is getting detached from other three globin chains. This detachment happens by breaking the Sol bridges which are formed in the tissue side. What are involved in Sol bridge formation? Carbamino compounds are involved in Sol bridge formation. Those Sol bridges get ruptured and carbon dioxide comes out. Not only carbamino compounds, even the histidine H plus would have gotten involved in some Sol bridge formation. That H plus also comes out. This H plus reacts with bicarbonate, which was so far transported in plasma, to form H2CO3. that H2CO3 in the presence of carbonic anhydrase becomes water and carbon dioxide, and this carbon dioxide will be exhaled out. This is what is happening in the lung side. So in the lung side, do you see a reciprocal binding of oxygen and carbon dioxide? Whenever oxygen binds, carbon dioxide has to leave, right? And that is called as Haldane effect. So tell me, what is Bohr effect and what is Haldane effect? Bohr effect is reciprocal binding of oxygen and H+. Haldane effect is reciprocal binding of oxygen and carbon dioxide. Bohr effect happens at the tissue side. Haldane effect happens at the lung side. So what is Haldane effect? It is reciprocal binding of oxygen and carbon dioxide. That is, deoxyhemoglobin will have higher affinity for carbon dioxide. Do you understand this? Deoxyhemoglobin will have higher affinity for carbon dioxide. The same is stated in Genong in a complicated way. Okay, so Genong says that in Haldane effect, at the same partial pressure of carbon dioxide content of a deoxygenated blood. At the same partial pressure of carbon dioxide content of a deoxygenated blood will be more than that of oxygenated blood. Yeah, that is called as Haldane effect. Let me draw this as a graph for you. So how is this graph drawn? This graph is drawn with what along x-axis and what along y-axis. Along x-axis, we have partial pressure of carbon dioxide. Along y-axis, you have carbon dioxide concentration. And you will see two curves. Okay, one curve is for oxygenated blood. The other curve is for deoxygenated blood. Okay, at the same partial pressure of carbon dioxide, let's have a partial pressure of 40 millimeters of mercury. At the same partial pressure of carbon dioxide, do you see that the carbon dioxide content of deoxygenated blood is more than that of oxygenated blood? And that's called as Haldane effect. So a quick recap on what is Bohr effect and what is Haldane effect. Bohr effect is reciprocal binding of oxygen and H+. Whenever there is deoxygenation, H+ binds, or whenever H+ binds, oxygen has to leave. So there is a reduction in the affinity of hemoglobin for oxygen on H+ binding, and that's called as Bohr effect that happens at the tissue side. Haldane effect is reciprocal binding of oxygen and carbon dioxide. What does Genong state? At the same partial pressure of carbon dioxide content of a deoxygenated blood is more than that of oxygenated blood. Okay, so that's about what happens at the tissue side and what happens at the lung side. Now, what is the effect of 2,3-BPG? We always say that 2,3-BPG reduces the affinity of hemoglobin for oxygen and it helps in unloading oxygen to tissues. We say that, right? 2,3-BPG reduces the affinity of hemoglobin for oxygen, helps in unloading oxygen to tissues. But we need to know why. It's because when hemoglobin is a tetramer with 4 globin chains placed like this, it is like you placing 4 coins nearby. And these 4 coins together will enclose a diamond-shaped cavity in the center. Look at this. This is hemoglobin, and in this hemoglobin you have alpha 2, beta 2. Okay, so these 4 globin chains enclose a diamond-shaped cavity in the center. And this diamond-shaped cavity is surrounded by parts of globin chain. And here, beta globin chain. Yeah, beta globin chain parts provide with positively charged amino acids, namely histidine H21 and lysine. Do you understand this? The central cavity is surrounded by parts of globin chain which provide with positively charged amino acids, namely histidine, H21 and lysine. So when they are positively charged, what about the charges of 2,3-BPG? 2,3-BPG, it is 2,3-bisphosphoglycerate. Phosphate is negatively charged, glycerate is also negatively charged. So 2,3-BPG is negatively charged and the central cavity is positively charged. So always one molecule of 2,3-BPG comes and binds to the central cavity and favors salt bridge formation. Salt bridge formation favors what structure I told you? TORT structure. TORT structure favors deoxygenation. And this is how 2,3-BPG reduces the affinity of hemoglobin for oxygen. So if you are asked, how does 2,3-BPG reduce the affinity of hemoglobin for oxygen? It is because 2,3-BPG binds to the central cavity, which is surrounded by parts of globin chain which provide positively charged amino acids, favoring salt bridge formation. Salt bridge formation favors TORT structure. TORT structure favors deoxygenation. That is how 2,3-BPG reduces the affinity of hemoglobin for oxygen. Okay. Now, what about fetal hemoglobin? We always say that fetal hemoglobin exhibits higher affinity for oxygen. And yes, your fetal hemoglobin has to exhibit higher affinity for oxygen because fetal hemoglobin accepts oxygen from maternal circulation, whereas adult hemoglobin accepts oxygen from atmospheric air. So fetal hemoglobin should be capable of accepting oxygen from relatively lower partial pressure of oxygen. That is why it exhibits higher affinity. But how does it exhibit higher affinity? It is because fetal hemoglobin is not alpha 2 beta 2, it is alpha 2 gamma 2. So what does it have? It has got alpha 2 gamma 2. The difference between beta chain of adult hemoglobin and gamma chain of fetal hemoglobin is, in beta chain, I told you they provide with histidine and lysine. In gamma chain, histidine is replaced by serine. So the central cavity is not surrounded by many positive charges. One positive charge offering agent, which is histidine H21, is replaced by serine. So there is less number of positive charges in the central cavity. So there is reduced affinity for 2,3-BPG. When there is reduced affinity for 2,3-BPG, what will happen to affinity for oxygen? Affinity for oxygen increases. So if you are asked, why does fetal hemoglobin exhibit higher affinity for oxygen? Your answer should be because fetal hemoglobin exhibits lower affinity for 2,3-BPG. And if you're asked, why does it exhibit lower affinity for 2,3-BPG? Your answer should be because fetal hemoglobin has got alpha 2 gamma 2. In gamma chain, histidine H21 is replaced by serine. So the central number of positive charges is reduced. Okay, so that's about what hemoglobin does at the tissue side, at the lung side. What is Bohr effect? What is Haldane effect? What is the effect of 2,3-BPG and how does fetal hemoglobin exhibit higher affinity? Now, let's learn about oxyhemoglobin dissociation curve. Okay, so how is this oxyhemoglobin dissociation curve drawn? Whenever you're trying to learn a graph, step number 1 is to find out what is along x-axis. Step number 2 is to find out what is along y-axis. Okay, in oxyhemoglobin dissociation curve, along x-axis, you have partial pressure of oxygen. So what is along x-axis? It is partial pressure of oxygen. What is along y-axis? It is percentage saturation along y-axis. If you think you might forget this in the exam, y-axis, y and percentage look similar. So along y-axis, it is percentage saturation. Along x-axis, it is partial pressure of oxygen. In such a graph, you're always worried about the position of the curve. you always want to know whether the curve gets shifted to the right. I'm going to show you a right shifted curve in red color. You always want to know whether the curve gets shifted to the right or the curve gets shifted to the left. Because shift of the curve to the right or shift of the curve to the left will tell you about P50. So what is P50? P50 is the partial pressure of oxygen at which it is 50% saturated. So if this is the normal curve, okay, and this will be the P50. So what is P50? P50 is the partial pressure of oxygen at which the hemoglobin is 50% saturated. Now tell me, what does it mean when you say that the curve is shifted to the right? Whenever you say that the curve is shifted to the right, you mean to say that the P50 is high. So tell me, what does it mean when you say the curve is shifted to the right? It means there is high P50. Whereas if you say that the curve is shifted to the left, tell me this is shift to the left. In this case, what has happened to P50? P50 is low. Now, can you tell me what does low P50 mean? When I say it is low P50, I mean to say even at such a low partial pressure of oxygen, it is 50% saturated. That's what it means, right? When I say P50 is low, I mean to say even at such a low partial pressure of oxygen, it is 50% saturated, which means its affinity is high. So P50 and affinity are inversely proportional. So can you tell me, what does it mean when you say that the curve is shifted to the right? Whenever you say the curve is shifted to the right, you mean to say that what is high? P50 is high or affinity is low. What does it mean when you say the curve is shifted to the left? It means P50 is low or affinity is high. Can you now tell me, when will you want the curve to get shifted to the right? When will you want the P50 to be high? And when will you want the affinity to be low? I want the affinity to be low whenever I want effective deoxygenation to happen to the tissues. Do you understand this? I will want the affinity of hemoglobin for oxygen to be low whenever I want effective deoxygenation to happen to the tissues. So when do I want effective deoxygenation to happen to tissues? Whenever there is hypoxia, right? Or whenever there is anemia. Whenever there is an increase in body temperature, whenever there is acidosis. So tell me, when will I want the curve to get shifted to the right? I want the curve to get shifted to the right whenever I want effective deoxygenation to happen. Example, hypoxia, anemia, increase in body temperature and acidosis. Let me tell you why for all these four causes. Let me start with hypoxia. Hypoxia because I say a person is hypoxic whenever a person's tissues do not get enough oxygen, right? And when I know tissues are not getting enough oxygen, my remedy would be to give more oxygen. How will I give more oxygen? By reducing the affinity, by shifting the curve to the right. Okay, anemia. Anemia means oxygen carrying capacity of the hemoglobin being low. Even if the carrying capacity is low, whatever is being carried should be given off to the tissues. How will I be able to give it off to tissues? By reducing the affinity, shifting the curve to the right. Increase in body temperature means there is an increase in the rate of metabolism. And whenever there is an increase in the rate of metabolism, I should support the increase in the rate of metabolism by giving oxygen. So I want the curve to get shifted to the right. I want the affinity to be reduced. Acidosis. In acidosis, my aim is to avoid further acid production. I know in anaerobic metabolism, always acids get generated. So in acidosis, to avoid further acid production, I want to avoid anaerobic metabolism. I should support aerobic metabolism. How will I be able to support aerobic metabolism? By giving off oxygen. Okay, so affinity is reduced, the curve gets shifted to the right. So what are the conditions wherein the curve gets shifted to the right? Hypoxia, anemia, increase in body temperature and acidosis. Now, how? Right? So, in the first three conditions, namely hypoxia, anemia, and increase in body temperature, the curve gets shifted to the right because in all these conditions, 2,3-BPG will be generated. Whenever a person is hypoxic, whenever a person is anemic, whenever there is an increase in the body temperature, glycolysis will be stimulated. And I told you in the session on glycolysis that 2,3-BPG is a byproduct of glycolysis. That 2,3-BPG reduces the affinity, shifts the curve to the right. Okay. Now, how does acidosis shift the curve to the right? That is not because of 2,3-BPG. Acidosis shifts the curve to the right because of Bohr effect. What is Bohr effect? I told you. Reciprocal binding of oxygen and H+. So, in acidosis, H+ ion binds. So, oxygen leaves. Do you understand this? In acidosis, oxygen leaves because of Bohr effect. So that is about conditions which shift the curve to the right. I hope it's clear to all of you. No point in just memorizing it. You should know that the curve gets shifted to the right whenever there is effective deoxygenation that is necessary. And conditions include hypoxia, anemia, increase in body temperature, and acidosis. First three conditions because of increased 2,3-BPG production. And the last one wherein there is acidosis, it's because of Bohr effect. Okay. So now, can you tell me when will the curve get shifted to the left? The curve gets shifted to the left whenever there is alkalosis or whenever there is decrease in body temperature. Okay. And though I told you alkalosis shifts the curve to the left, there is an exception here. And the exception is acclimatization. Okay. So, in acclimatization, in spite of that being alkalosis, the curve gets shifted to the right. So, let me tell you what is acclimatization. What is acclimatization? Acclimatization includes all adaptive changes which happen when a person is slowly getting exposed to hypoxia. On the other hand, what happens when a person is quickly getting exposed to hypoxia? The person hyperventilates. When a person hyperventilates, the person washes away carbon dioxide. When the person washes away carbon dioxide is a source of acid. The person is getting rid of a source of acid that causes alkalosis. And this alkalosis is detrimental because your central chemoreceptors, your central chemoreceptors which are present in the medulla respond only to an increase in hydrogen ion concentration in the CSF. And when you get quickly exposed to hypoxia, when you hyperventilate, you end up in alkalotic condition. In alkalotic condition, there is no hydrogen ion increase in the CSF. So, central chemoreceptors will be depressed. When central chemoreceptors are not getting stimulated, then the respiratory center will be depressed, which is dangerous. Yeah, not just that, whenever there is alkalosis, what will happen to the curve? I said the oxyhemoglobin dissociation curve gets shifted to the left. When the curve gets shifted to the left, you know that the P50 is low and the affinity is high. What will happen when there is an increase in the affinity? When the affinity of hemoglobin for oxygen is increased, hemoglobin might be able to accept oxygen from the low partial pressure of oxygen in the atmosphere. But what will happen when the same hemoglobin tries to give oxygen to tissues? Because the affinity is high, it will not be able to give oxygen to tissues. So tissues will suffer from hypoxia. So we are not happy about the curve getting shifted to the left too much in hypoxic exposure. Do you understand this? So can you tell me why are you worried about quickly getting exposed to hypoxia? You hyperventilate, there is alkalotic pH which is dangerous. Why is alkalotic pH dangerous? Central chemoreceptors do not get stimulated, respiratory center gets depressed. Also, alkalotic pH shifts the curve to the left, increasing the affinity, and hemoglobin will not be able to give oxygen to tissues. Okay. Whereas what happens when a person is slowly getting exposed to hypoxia? Even in this case, the person hyperventilates. Even in this case, there will be alkalotic pH. Okay. And this alkalotic pH will shift the curve to the left only because of Bohr effect. I told you, right? An alkalotic pH, when there is no hydrogen ion, when hydrogen ion leaves, it binds oxygen. Okay. So alkalose is shifting the curve to the left is only because of which effect? Bohr effect, which is only a momentary change. But in due course, alkalosis stimulates glycolysis. Okay, alkalosis stimulates glycolysis. Glycolysis provides 2,3-BPG. And this 2,3-BPG reduces the affinity of hemoglobin for oxygen and it shifts the curve to the right. That's very good. Why is it good? Because when the curve gets shifted to the right, deoxygenation will happen to the tissues. Okay, so this is one of the adaptive changes which happen in acclimatization. What is one of the adaptive changes which happen in acclimatization? In spite of there being an alkalotic pH, the curve gets shifted to which direction? The curve gets shifted to right. Why does it get shifted to right? It gets shifted to right because of production of 2,3-BPG. Got it? So this is about oxyhemoglobin dissociation curve. So in oxyhemoglobin dissociation curve, we have partial pressure of oxygen along x-axis, percentage saturation along y-axis. We always want to know the position of the curve. We want to know whether the curve is shifted to the right or to the left because that tells you about P50. P50 is the partial pressure of oxygen at which it is 50% saturated. Shift of the curve to the right, meaning there is high P50 and low affinity, which will favor deoxygenation to happen to tissues. And that happens in hypoxia, anemia, increase in body temperature, acidosis, and acclimatization. Shift of the curve to the left means there is low P50 and high affinity that happens in alkalosis and reduction in body temperature. Okay, so that's all about oxyhemoglobin dissociation curve. And this is all I wanted you to know as far as hemoglobin and myoglobin are concerned. To summarize all that we have discussed so far, myoglobin is a monomer, hemoglobin is a tetramer. In myoglobin and in hemoglobin, histidine E7 provides a hindered environment because of which we escape from carbon monoxide poisoning because histidine E7 does not allow carbon monoxide to bind. Okay. Second fact that I told you is about the taut structure and relaxed structure. Hemoglobin exhibits taut structure and relaxed structure. Taut structure favors deoxygenation and relaxed structure favors oxygenation. Okay. Then I told you about cooperative binding. What is cooperative binding? Binding of one oxygen molecule to one Fe2+ favors binding of another oxygen molecule to the next Fe2+. That's called as cooperative binding. Then we learnt about what happens at the tissue site, wherein I told you about Bohr effect. What is Bohr effect? Reciprocal binding of oxygen and H+. What is Haldane effect? Reciprocal binding of oxygen and carbon dioxide. Or in other words, deoxyhemoglobin exhibits higher affinity for carbon dioxide. That's called as Haldane effect, which happens at the lung side. Bohr effect happens at the tissue side. Then we learnt about 2,3-BPG, which reduces the affinity of hemoglobin for oxygen by binding to the central cavity, favoring salt bridge formation. Then I told you about fetal hemoglobin exhibiting higher affinity because fetal hemoglobin has got alpha-2 gamma-2, wherein histidine H21 is replaced by serine. We then learnt about oxyhemoglobin dissociation curve, conditions which shift the curve to the right and conditions which shift the curve to the left. Most of these conditions you would know. Shifting to the right because of hypoxia, anemia, increase in body temperature, acidosis. Along with that, also remember acclimatization. Shift to left happens whenever there is alkalosis and reduction in body temperature. Okay, so let's work out few MCQs now. Fe2 plus is attached to which of heme? F for F, Fe2 plus is attached to histidine F8. The amino acid which is responsible for the hindered environment protecting us from carbon monoxide poisoning is histidine E7. Carbon monoxide displaces oxygen away, reduces oxygen carrying capacity, so it causes anemic hypoxia. This I've already told you in the session on electron transport chain. All electron transport chain inhibitors cause histotoxic hypoxia. Carbon monoxide poisoning causes anemic hypoxia. 2,3-BPG facilitates which structure? 2,3-BPG sits, favors Saul bridge formation, which is taut structure. So it favors taut structure of hemoglobin. Anemia shifts the oxyhemoglobin dissociation curve to right. The amino acid of globin chain, the same question in the form of MCQ, which provides hindered environment, E7. All of the following are true about Bohr effect except. What is Bohr effect? Deoxygenation, yes, it increases the affinity for hydrogen ions. This is true. Decrease in the affinity of hemoglobin for oxygen on H plus binding. Yes, when H plus binds, oxygen has to leave. Does it happen in the lung side? No, it happens at the tissue side. Does acidosis shift the curve to the right? Yes, that's because of Bohr effect. Binding of carbon dioxide to hemoglobin forms carbamino compounds which are negatively charged. That favors Saul bridge formation. Saul bridge formation favors taut structure. So carbon dioxide binding will shift relaxed structure to taut structure because it is negatively charged. Okay, answer is choice B. All the following causes shift of oxyhemoglobin dissociation curve to right except. Right happens always except what? Alkalosis. We know that, right? 2,3-BPG reduces affinity, shifts it to the right. Hypoxia and anemia for the same reason will shift it to the right. All the following cause shift of oxyhemoglobin dissociation curve to right except. Again, alkalosis. But here, you should know acclimatization in spite of there being alkalotic pH, shifts the curve to the right. Fetal hemoglobin exhibits higher affinity for oxygen because it exhibits lower affinity for 2,3-BPG. Total number of 2,3-BPG bound to one molecule of hemoglobin. What do you mean by one molecule of hemoglobin? That tetramer. This tetramer includes only one cavity. In one cavity, only 1,2,3-BPG can bind. Do you understand this? There can be hypoxia, there can be anemia, there can not be hypoxia, no anemia, whatever it is. But there is only one central cavity to which only 1,2,3-BPG can bind. They might try to confuse you, right? So the moment you see hypoxia, okay, you will think, okay, there should be deoxygenation. Let me allow more 2,3-BPG to bind. I know that there is a tetramer, which is hemoglobin. So let me answer it as 4. Right? That's what we tend to think. But please remember, it binds to the central cavity. There is only one central cavity in a hemoglobin molecule. So it is always 1. Case-based MCQs. A person in his mid-40s wants to try skiing at 3,950 meters height. So there will be hypoxia, partial pressure of oxygen in the atmosphere will be low, and is prescribed acetazolamide. You know that, right? Acetazolamide is prescribed for mountain sickness. Why? It's because acetazolamide causes metabolic acidosis. Why are you trying to induce metabolic acidosis? Because when a person quickly climbs uphill, as I told you, there will be alkalotic pH. And this alkalotic pH is dangerous for two reasons. One is central chemoreceptors do not get stimulated, respiratory center is depressed. The other one is alkalosis shifts the curve to the left, which means deoxygenation will not happen. For these two reasons, you have to induce metabolic acidosis. How will you induce metabolic acidosis? By giving acetazolamide. So how does acetazolamide cause metabolic acidosis? Because as you all know, acetazolamide is a carbonic anhydrase inhibitor. And this carbonic anhydrase is responsible for bicarbonate reclamation in the PCT. Yeah, proximal convoluted tubule reabsorbs all bicarbonate with the help of carbonic anhydrase. So acetazolamide does not allow bicarbonate to be reclaimed, and bicarbonate will be lost in the urine. Without bicarbonate, which is a major plasma buffer, metabolic acids will start accumulating. So acetazolamide causes metabolic acidosis, which is good, because respiratory center will be stimulated and the curve will get shifted to the right. That will help in deoxygenation to tissues. Do you all understand this? So why do you prescribe acetazolamide for mountain sickness? Because it causes metabolic acidosis. Why do you want metabolic acidosis? Because that will cause the oxyhemoglobin dissociation curve to get shifted to the right. Okay. So that's the right answer. So do you all understand how clinical biochemistry can be? Yeah, no point just memorizing, okay, I have to give acetazolamide when a person quickly climbs uphill. I don't know the mechanism, right? This is almost like a quack treating a person. So you as a medico should know why are you doing this. You should know exactly acetazolamide is given because it induces metabolic acidosis and it helps the curve to get shifted to the right. Image-based question. This is a previous INI CET question. The exact image was given. Identify the left curve given the fact that the right curve is of adult hemoglobin. So adult hemoglobin curve is sigmoidal. And the curve that is given to you is hyperbolic. And which is the hyperbolic curve? This is of myoglobin. Okay. So what do you mean by hyperbolic curve of myoglobin? It means it is shifted far towards the left. What does it mean it is shifted far towards the left? It means its P50 is very low. What if its P50 is very low? It means its affinity is high. When its affinity is high, it will not be able to unload oxygen to tissues. It can store oxygen, but it cannot unload oxygen to tissues. That is why myoglobin is used as a storage form. And hemoglobin is used as a transport form. So if you are asked, why is myoglobin used only as a storage form, not as a transport form? Your answer should be because myoglobin P50 is very low, close to 8 millimeter of mercury. So it never unloads oxygen to tissues. It can only be used for storage, not for transport. Okay. So what is answer? The answer is myoglobin because the curve is hyperbolic. I hope you enjoyed this session. I hope you understood all about Bohr effect, Haldane effect, about 2,3-BPG, about oxyhemoglobin dissociation curve. So I'll meet you in the next video wherein I will be discussing about electrophoresis and chromatography. Yeah, thank you.